Hi everyone, welcome to the last breakout session of the day. Before we get started, I'd like to just remind you to fill out the survey or the ballot that's on the website for the best poster, because we're going to be picking candidates soon. So that will be exciting when we hand out prizes. Okay, so moving on to the last breakout session of the day, we have Dr. Ryan Iutzi here from Analog Devices. And he's also a nanograd, and he'll be talking about his work at Analog Devices. He did his Ph.D. at MIT with Professor Eugene Fitzgerald and in quantum tunneling devices. And he's moving on to talk about how he can push the boundaries of Moore's law and how nanotechnology is enabling that, and his work and how he's making that happen. So with that, I'd like to welcome Ryan Iutzi.
Okay, well, thank you very much. And since I'm the last presenter of the day, I'll take the opportunity to thank our great organizers for this conference. This has been a fantastic conference, very well run, very interesting. Even the graphics are pretty impressive, I think. So, I work in the Advanced Development Group at Analog Devices. We are one of the largest semiconductor companies in the world. And this talk is on life after Moore's law. And maybe that sounds a little dramatic, but this talk, I'm not going to say that Moore's law is over, but what I'm going to say is that the landscape of electronics and the semiconductor industry is changing in a way that there's more to life than Moore's law. And this is a very interesting change. I'm going to talk about sort of my opinions on it, but more importantly, I'm going to talk about what it means for all of you. I don't know how much you know about Moore's law, but I know it's commonly talked about in semiconductor talks. It's the basic simple idea that transistors get smaller. They get smaller because making them smaller makes them faster, more energy efficient, and cheaper. And we're at a point now where 14 nanometers minimum feature size is in production and 10 nanometers is in development. And this thing just keeps going and going and going. And it's still really the same fundamental technology. It's a silicon MOSFET transistor. And it just keeps getting smaller and better. But this can't really continue forever. I know for decades people have been saying this can't continue. But this time I really mean it, because look we're at 7 nanometers, 5 nanometers. We can't get much smaller than this. I mean, at some point we're going to be down to the size of one atom. And that's really a limit. Now, there's things we can do. We can switch to different materials, and there's ways we can continue to innovate. But the point is we can't go much smaller. So is that a problem for nanotech? Not necessarily. But before I talk about that, let me tell you about one other problem with Moore's law. Because I just said things get cheaper as we get smaller. But that actually stopped at the 28 nanometer node. That was the first node ever that from there on out, transistors actually get more expensive per transistor on a chip. And the reason is because the lithography equipment is getting too complicated, the yields are low, the development costs are high. But this is an unprecedented occurrence, and in my opinion, it's going to change the landscape of the industry, because it's no longer just a no-brainer to go to a smaller size. You have to weigh the fact that it's going to be more expensive. Now, I'm sure for the most high-performance computing devices, you're still going to want to do it because you need that high performance. But we might enter a realm where we're only going to see all but a few high-performance things on the cloud that go to these advanced nodes, and others are going to maybe hang back around 28 nanometers. Who knows? So what does this mean? Because I know when I was in nano at Waterloo, I was in the nanoelectronics track, and the sort of general theme was always Moore's law, that as we make transistors smaller, it gets better. And now I'm standing here saying we can't make them smaller, or it's not economical to make them smaller. So does that mean we're done? Well, no, I actually think that this is the best opportunity ever for nanotech. And the reason is because we're entering a new realm where it's not just about computing anymore. It's not just about having a computer that computes faster, that runs Microsoft Excel faster, that runs Facebook faster. We're going into a new realm where electronics are not just going to be in laptops, or even smartphones for that matter. They're going to be everywhere. We call this more than more, or the Internet of Things. The idea that electronic chips are going to be driving our cars, sensing the world around us, even on our clothes, monitoring our health. This is very different because they no longer just need to compute. They no longer just need to run programs. They actually need to interact with the world around them. They need to sense physical, real phenomenon. They have to convert that into an electrical signal. They need to communicate that information with other devices. And in some cases, they need to do this at low power. Or they need to do it at high power. There's a whole myriad of different functions. And the real interesting thing about it is that each function has a different set of requirements. And it turns out that in a lot of the cases, each function requires a different fundamental innovation on the nanoscale. So this whole time when we talk about nanoelectronics, it's always been trying to replace the CMOS transistor, trying to replace this one device. And we had all these people doing this stuff, but they were all doing it so that they could be the one winner that replaces silicon. And guess what? It never happened because we're still using silicon. But now we don't have to do that because now choose your application. It's something new. It doesn't have to be the smallest device, but it needs to do something novel, and that means that we need some sort of innovation that often is on the nanoscale. So I think that's actually a big opportunity, and I wanted to use this talk to sort of convince you of that, to give you a few examples of the various types of fundamental technologies that need to happen to enable this next wave. And I could talk for 3 hours about all the different things, so instead I'm going to restrict it to stuff that I've dealt with directly. And I'm going to tell the story in terms of 2 case studies to make it fun. And the first case study will be autonomous vehicles, because we all know what that is and we all want that, right? Like we all want to wake up in the morning and just our car drives us to work. I can sleep or shave while we're driving. It would be amazing. But a lot of things have to happen for that to really be reliable. For one thing, the obvious one is that the car needs to be able to detect other vehicles and pedestrians around it. And so this is the first challenge, because we need automotive radar, or we need some sort of electromagnetic wave that's going to detect the car. It might be radar, it might be LiDAR, but the point is it's probably going to be pretty high frequency, because we need the bandwidth to be able to do this reliably. It's so high frequency that silicon CMOS, which is fast when it comes to doing logic, but it's not going to be fast enough to condition a signal that's running at hundreds of gigahertz. And the reason is because a silicon CMOS device has a gate. It has a high input impedance. And you can make it faster by making it smaller, but at some point you need to do something different. So the first example isn't going to be too different from silicon CMOS. It's actually going to be a much older technology. The BJT transistor was actually invented long before the MOSFET. And we switched to CMOS because it was lower power, it was better for logic. But now we're in this application where we want high speed. It actually makes sense to go back to the BJT because it's faster. It doesn't have a high input impedance. It's basically electrons moving from emitter across this base to collector. And we turn it on and off by switching the voltage across this base. And so this is an example of a device where its novelty doesn't come from just taking something and making it smaller, but instead changing the materials. So in this particular case, this was the DOT7 project, which achieved frequencies of many hundreds of gigahertz. It did it by putting a silicon germanium base, and they weren't the first people to do it, but this is just one example. They did it, this technology does it by putting a silicon germanium base in. So this is a completely different material, and you can see it's only about 10 nanometers thick or so in this image. And not only is it a material, but it's actually got a graded concentration. So the concentration of germanium starts really high, and then it gets smaller and smaller. So this tiny little feature, every single layer of atoms, the subsequent layer has a few less germanium atoms than the previous one. Do you have any idea how hard that is to control? That is really hard to control. And you have to do it in this small little area. So you have to do selective epitaxy to make this work. You have to literally grow this atomic layer by layer. And then there's all these other problems that happen as you try to shrink a device like this. You start to get fastest that form. You start to get strain energy minimization, surface energy minimization. So there's a whole different realm of problems here that are different than the same old set of problems that we had when we were just trying to scale transistors. And it requires new knowledge and new work. And one thing that's nice about this one is because it's still close to silicon, it's still on a silicon substrate, you can actually still put CMOS right beside it, and we call this BiCMOS. And it's no surprise that Analog Devices has a lot of proprietary BiCMOS technology, and we're one of the best in the industry at this. So that's the first example. Another thing that autonomous vehicles need to be able to do is communicate with other vehicles on the road to let them know their position and location. At least ideally, we would like to have that. Now, that's a pretty cool idea, because if you imagine a world where everything is an autonomous vehicle, then we really don't need stoplights anymore, because these cars are just communicating with each other, telling us where they are. They're just going to have some algorithm, and they're just going to drive through the intersection. It's going to be terrifying, but in theory it should work. Of course, we just have to make sure that there is no lag in the communication between these vehicles. That would be very bad. So your phones use 4G, that's not fast enough. But the next standard is 5G. And it's believed that that would be fast enough to make this work. And we don't entirely know exactly how the 5G standard is going to work yet. But what we do know is that it's going to require high power and high frequency, which is often seen as a trade-off. Silicon breaks down at a certain voltage because of its band gap. If you look at the parameters of silicon, it's got 1.1 electron volt band gap, and it breaks down under a certain field. So we have to find a new material. And I won't go too much into all the different materials, but it turns out that gallium nitride can probably do the job. The reason is because it's a 3-5 semiconductor. It's got a gallium atom bonded to a nitrogen atom. It's got a very large electronegativity difference between those two atoms, and that results in a very large band gap. And because it has that large band gap, it has a high breakdown field. Yet somehow it does all this without having a low mobility. It actually has a higher hole mobility than silicon. So it's capable of both high speed and high voltage. And this is an enormous opportunity. And this is an interesting area of research and development. So here's what a device would look like. And so see, now we're drifting even further away from silicon. But these devices aren't necessarily going to be smaller than silicon. They're novel in their own way. They're novel because they're a new materials challenge, because there's all sorts of different things. And they're still on the nanoscale. But there's a whole set of new nanoscale phenomenon that we have to understand to make them work. What's really cool about GaN technology is that if I combine it with aluminum gallium nitride, because of that large electronegativity difference between those two columns in the periodic table, it has this enormous polarization field. The result is that if I put GaN next to AlGaN, it creates a field that changes the bands such that I get this enormously bent region. And this happens on such a small scale that it forms a quantum well. So the result is that you get what's called a 2D electron gas, a two-dimensional electron gas. And this means that this device can be very fast because, first of all, I put all these electrons in one spot. Normally I have to dope it and put all these dopants in, but then I have all these ionized impurities that are going to scatter. But here I pull it off without putting any dopants in there. The second reason is that I put so many electrons in there that they can actually screen each other from defects, which normally lower the mobility. So the point is that this is a potential avenue that can really get high speed, high voltage, and enable 5G communication. Of course, it comes with its own brand new set of problems. Here's an example where the drain starts to form a pit over time after it runs. These are the same growing pains that silicon CMOS had to go through over many decades while people figured it out. And now this is just one new technology among many, but it has the same need for all sorts of people working on it and solving these problems. And at ADI, at Analog Devices, we're interested in this stuff, but we don't just develop these things on our own. Some of these problems are on such a large scale that we really need to collaborate with others. We actually, on this sort of area, we collaborate very heavily with MIT. And I wanted to bring that up because I was at the industry panel this morning, and I heard a lot of mixed opinions on how useful industry-academia collaborations can be. And there was one really good point that industry has a different goal. They want to solve the problem. University wants to do it in a way that's never been done before. And there's a bit of a disagreement there. I think that's true. But for a big cutting-edge company that's constantly trying to push the boundaries, you have to think 10, 15 years out sometimes. And on that sort of time scale, the solution to the problem is going to be something that hasn't been done before. So the result is that gets resolved and it becomes useful to have these collaborations. We celebrated our 50th anniversary last year. The high-tech company doesn't stay around for half a century unless it's thinking many years out, and you need to be collaborating with universities to do that. And the Waterloo Institute for Nanotechnology would be wise to continue to have these kinds of collaborations, in my opinion. I'll give you one more example of the Internet of Things, a completely different example. And these are really just two random examples. There's plenty. Let's say we're talking about some sort of wearable gas sensor or remote gas sensor. Maybe it's on you, it's designed to check air quality, or it's designed to warn you if there's a dangerous gas nearby. So now we have a totally new set of requirements. You're going to see that's going to result in a totally new set of materials and technologies that we need. It's not going to be silicon CMOS necessarily. So the first thing is that we need to sense gas. So First I was showing you we need to be faster, then we need to be higher power. Now we're getting right at the front of the signal chain where the sensor is. This is the chip that actually has to interact directly with the environment. So you can imagine it's going to be the wackiest material of all. Not too wacky, but the example I'm going to use is metal oxide semiconductors. And I wanted to bring this one up because we actually did this here at Waterloo as part of our nano design project. And the way we made it was we used tin oxide and titanium dioxide nanoparticles. And the way it works is the gas reacts with the nanoparticles, and because they have a high surface area, they can inject electrons in and change the resistance of the device. And so we made this device and it works. Here's a cool picture of it on a large scale, and we're slowly zooming in as we go all the way to the nanoscale, and you can see the individual nanoparticles in the last picture. And this thing works successfully. You can see as we in this case, we were testing on ethanol. We exposed it to 100 ppm and you get a signal. You expose it to a little more ethanol, it gets a higher signal. So this is an example of something that involves new materials. It involves nanotechnology, and it needs to address this one specific need, and that's what it's for. It's niche, but it's useful. And now, to contrast with the previous example, we need something that was high power. Well, if we have a remote sensor, it needs to be on your clothes. It might need to run a long time without having a lot of battery charge. So it really needs to be on the other side. It needs to be low power. So how do you make something low power? And I'll use the example of logic. You know, in a case like this, we might not be able to just have all the processing done in CMOS because it's going to consume too much power. So how do we do logic at lower power? Well, I spent a lot of time at MIT doing stuff like this. And one way to do it, and there's many ways to do it, but one way to do it is to use quantum tunneling. And so this is a system that involves indium arsenide and gallium antimonide and a junction between the two. This system is interesting because the conduction band is actually lower in energy than the valence band of gallium antimonide. So classically, the way a transistor works is we have these electrons that have to hop over a barrier. And by switching the device on and off, you're just making that barrier smaller and more can hop over. That's really all a MOSFET is. But on a nanoscale, remember, these aren't necessarily just particles, they're waves. So in a system like this, they can actually quantum tunnel across. And so we have this current. Now all I have to do, so I'm just going to draw the current as a red arrow. So all I have to do is apply a tiny little voltage to bring these bands down. And now there's nowhere to tunnel to because it's in the band gap. So if you can imagine just toggling this switch on and off with a little bit of voltage, I can rapidly switch between a lot of current and a little bit of current. And I made this thing. Here's a tiny tunnel barrier that's only a few layers of atoms. And it works, sorta. So it works because you can see here the bands are aligned and tunneling's allowed, and here the bands are not aligned and tunneling's forbidden. It has, in my opinion, though, this has a long way to go. And I won't get into the details. I've given lots of talks on this before on all of the challenges. But it's something to be aware of, and it's something that's interesting. There's several other ways to get low power electronics. We don't know what the winner will be yet, but that's part of what makes it interesting. So I want to finish the talk with saying, imagine we figure all of these things out, which we haven't done yet. But imagine in all of these applications, we figure out the best technology, we get it to work, we figure out a way to make it reliable. We're still not done. Because now we have to go up to the systems level and find a way to integrate all these things. Now, in the past, that's always been easy. You have a chip, you have a few other chips, you just put them in a package, you wire them together. But in these new sort of niche areas, it turns out that more often than not, you can't just do it that way. Let me go back to the example of the self-driving car. I just said we need a SiGe by CMOS chip and a GaN chip, and they both need to be fast. So how are we going to wire these two together? Are we just going to put them side by side and attach them with wires, maybe use a wire bond, which people have been doing for decades? But the problem is that these wires are going to be enormous. From our nano perspective, these wires are huge. They're going to have an enormous capacitance, and they're going to slow down the device. In other words, every time this wave is going up and down that we're trying to process, we have to wait for electrons to fill this enormous wire. It's never going to be able to do it in time. It's going to completely destroy the device. So to make these two chips work together, they have to be connected on a nanoscale. They can't just have nanoscale components. They have to be pretty much connected on a nanoscale. Maybe you won't be able to do it on a nanoscale, but you have to do it as small as possible for performance. But what about the other example? I mean, speed is not really that important with a gas sensor, right? But there's still reasons why everything needs to be close together. And just economically, let's say I have a gas sensor that tells you the air quality and warns you if you're in a bad air quality place. You're probably not going to buy it if it's just this standalone thing that you have to put in your pocket. You're probably only going to buy it if it's a module in your iPhone or if it's on your watch or if it's something that's easily integrated. So it needs to be small. And so in this area, form factor is everything. And for the same reason, you have to have everything as closely coupled as possible because there's actually a very limited amount of real estate on these things, especially if you're trying to put hundreds of different sensors on it. It turns out that really, no matter the application in the more than more era, you have to figure out a way to put it all together. And normally, putting things together is where you no longer have to worry about material science and thermodynamics. Normally, you have to worry about nanoscale thermodynamics when you're making the components. But even up at the systems level here, putting it together, we're still limited by thermodynamics and a lot of physics problems. I just showed you why we can't do this on a large scale. So you might think, well, let's just go to the smallest scale possible because then everything will be great. And the smallest scale possible is just having a single crystal with the different materials. Say I'm trying to combine GaN and silicon, have a single crystal where it's just all one piece. And this is an active research area, but it's not that simple. So here's an example where I tried to combine gallium arsenide antimonide with gallium antimonide so I can have two different devices. But you see all these black defects everywhere, and the reason is because this material has a different lattice constant. So it's going to form dislocations which are going to try to relieve the strain. And the result is that they're everywhere, and holes and electrons just recombine there, and the device doesn't work. You can play tricks though. You can, in this particular one, I was trying to combine indium phosphide and indium gallium arsenide. So in a perfect world, I could have an indium gallium arsenide device up here, and then a small wire that goes down to an indium phosphide device down here. And I made it work by grading it very slowly with indium arsenide phosphide. So basically what I did was, I let it form these dislocations, but I made sure that it happened slow enough that these dislocations just travel horizontally and relieve the strain. And then the few that exist go up to the surface, but not a lot of them do. And the result is that you can see all these horizontal lines, but the top surface is actually free of dislocations. So this is an example where you can have two materials that might be able to work when they're connected pretty much on the smallest scale you can do. It turns out, though, these still have dislocations. You just can't see them in this cross-section TEM. And the problem with this area is that it just hasn't yet achieved the defect densities low enough for this to work. And then there's this middle area on the length scale, sort of a micron scale. And this is where I think we might start to see success first. So one example here is just, what if we just cut it into the smallest pieces possible? How small can we cut it? I don't know. Maybe we use lithography. Maybe we use a laser saw. You know, these are all questions. And then you take a stamp and you just peel them off, transfer them, and then place them on the other chip. So in this example, maybe this is like maybe this is our GaN, and maybe this is our silicon. So it's not ideal because circuit designers can't just design GaN and silicon devices wherever they want. They have to design it so their GaN transistors are confined to these square areas and silicon everywhere else. We're putting constraints on the system, and we're putting some speed constraints. But it's a step in the right direction. Of course, this has its challenges too. How are you going to get a good yield? I mean, this seems pretty wacky taking this plastic stamp. But we're open to anything that might work. The point is, we don't know yet which integration scheme will work, and in a lot of these areas, we don't know for each individual application what technology is going to work. I mean, 5G is supposed to be coming out pretty soon, but it's still debated on what the material of the semiconductor is going to be. But the point is, it's, to me, a more fun game to play now because it's no longer just this one winner, silicon CMOS, and we're all trying to replace it. Instead, it's choose your function and choose your junction, as someone from, I think, Raytheon once said. And whatever the application is, you can go all the way down to the material scale, to the nanoscale, and innovate there. It's no longer just foundries, necessarily, producing one or two processes, and then circuit designers over here working on something and just using their technology. Newer companies, if they really want to excel in this industry, I think have to start incorporating both. They have to have circuit designers and materials people under the same roof. And that's what we have at Analog Devices. And for all of you, I think it's an opportunity because if you want to get in this area, I think we should start seeing more opportunity soon and more need because we no longer have one problem to solve, we have hundreds of problems to solve. So that's my opinion on it. And I hope you enjoy my talk. At this point, I'll open the floor to any questions. One question? Yeah, we're an interesting company because we have no single department that we call R&D. We sort of spread R&D throughout. The advanced development group is under the manufacturing wing, so we focus mainly on process development. And then we have R&D units under various application areas, and then we sort of work together to try to come up with processes that match sort of the circuit designs that we want to do. And then in recent times, we developed Analog Garage, which is a new initiative that sort of acts as sort of an additional R&D unit, but it actually sort of acts like almost like a VC within the company where anybody can propose an idea and then they'll fund it. So yeah, we have a kind of unique approach to R&D where we actually have our R&D people kind of spread out in all units across the company.
With that, I'd like to thank Iutzi. And of course, he gets a goose too.
Oh, thank you. It's going to fly south with me back to America. Thank you very much.